Thanks for joining, everybody, and welcome back to week 2 of Introduction to Data Science with Lambda School. And we're so happy to have you all with us, and hope you've been enjoying our material so far. Very brief reminder is that this is just our 2-week, 8-hour really intro course, 8 hours of lecture. The full course is 2 hours of lecture 4 times a week, and it's starting November 5th. So we hope to see you all there, of course. This will run Tuesday through Friday this week, and the process is all the same. So any questions about standard form assignments, ask those in chat, and the PM will help. So without any further ado, do you all see my desktop okay? I will listen. All right, great, thank you. By the way, it is great as an instructor to have participation. So I know there's too many of you you can't unmute you're in a webinar, but please do keep chatting and typing and interacting. It's part of the learning process. This is your learning experience. So what are we talking about today? Well, we are talking about linear algebra, and I went ahead and found I don't know if this still counts as a cool picture or not, but I'm going with it. We are entering the matrix. We are going to deal with some of the real and significant math that powers what we then go on to do, the cool things we can do with statistics and data science. And you might already know a little bit about this. Let's even sort of as a poll. I've studied linear algebra before. Let's just do this as a yes, no. And I'll make it anonymous even, so please, everybody respond. Apparently, I have to accept the terms of the poll and invoke the poll command again. Thanks, simple poll. That was convenient. All right. Whatever you answer, by the way, it's fine. I know that we are covering a lot of material, and you might find that you have to go back and review. That's why I should drop this link even. That's why we give you the notebooks. That's why we record the lectures. This is our learning model. We cover a lot of ground, but we cover it from first principles in the sense that if you've not seen it before, you might have to go back and look at it a few times, but it's there for you, and we are there for you to answer those sorts of questions. So that said, what are we doing here? Well, even if you're a no, you've actually already seen some things kind of about this. You know, you've seen some Python data structures like lists. So offhand, any thoughts on what a list would be like? Like what sort of thing is a list kind of like in linear algebra? Anybody know any of these yeses here? Yes, a vector. Now, array would be like the sort of computer science way to talk about it. And that's another very valid way to think about it and thinking about memory addresses. We're not thinking about that now, though. We're thinking about numbers. And so it's a lot like a vector. So what is a vector then? So you've been working a little with Python lists. What are vectors? Well, there's a few ways to talk about vectors, and actually an important way, and a way that a lot of linear algebra is usually taught, so a way that we have here is the geometric picture, because you can have geometric pictures, right? That's why professors like teaching these things, right? So, well, how do we make pictures with good old matplotlib? And I'll go ahead and even rerun this code live, and it should remake. This code was courtesy of our very own Susanna, who's here on the call, our section lead. So feel free to ask her questions. That was a warning if I trusted Susanna. I think I do. So what we have here is these are vectors, and this is, as I said, the geometric picture, the picture of 3 vectors. And what are these vectors? Well, they're helpfully colored. Yellow, red, and blue. And exactly, in two-dimensional vectors, the natural geometric interpretation is direction and magnitude. And so we have different sorts of offsets and ways to them. Now, that said, the way we're actually plotting these is not direction and magnitude. There's an equivalent, not an equivalent, well, there's another way to do it. What sort of coordinates are these called? There's a hint, it's named after an old dead French guy. Cartesian coordinates, yep. So we're saying, okay, draw a yellow line from 0, 0, the origin, to 0.5, 0.5. And that will let us see this line here. It's a yellow line from 0, 0 to 0.5, 0.5. Draw a red line from, again, the origin. The origin is just 0, 0. That's what we call it. It's just where things naturally begin, and that's where vectors begin. And it goes to 0.2, 0.1, or to 0.1, 0.3 for blue. And this is a perfectly valid, good way to specify vectors, and this is what Arrow expects. And I think this is what we'll be using throughout. You can use something called polar coordinates, in which case you specify a vector as the direction, as an angle, usually called theta, and then the magnitude. If that was literally Greek to you, the theta and everything, that's fine. Don't worry about polar coordinates right now. But if you have studied this before, just know it's another way to address these things. But this is what a vector is. It's just a line, right? And why does it take two numbers to specify it? Can anybody, let's think about, whether you're using Cartesian or whether you're using polar coordinates, and we'll stick with Cartesian. We've got two numbers here to specify it. And we're also in two dimensions. Does that feel like a connection to people? Yes, this is not a coincidence, exactly. And our pictures, because it's the easiest to draw pictures, our pictures are going to be two-dimensional. But what makes this powerful, if you're wondering, oh, big deal, it's a yellow line, well, we're going to use nice small vectors and matrices because that's what we can sort of fit in our head and make pictures of. But we're going to apply these techniques, not today, sadly, but if you join us in our full course, we will apply these techniques to much, much larger dimensionalities, and they still work there. You just can't make nice pictures. And these dimensions can reflect all the different, say, aspects of some piece of data, all the different features. So I'm staying on this picture a while because it's important, but I should move on. Any questions so far? Does everybody have a vague idea? Okay, a vector, it's a line. If that's your mental picture, that's an okay place to start. It's a length or a magnitude, and it's pointed in a direction, and you can specify it with these coordinates. Okay, now here's the point I made at the beginning, so I won't spend too long on it. If we want to express it in Python code, well, we can just make some Python lists, and there we go. Now we've got our vector yellow, our vector red, and our vector blue. And these are coordinates that are the end point where the arrowhead is of the vector drawn from the origin. This is like the code way to talk about this picture, but it's equivalent, and we're using Python lists. Now, what about math? Well, yet another way. So we've got plots, we've got code, and we've got math. You will have to do a little bit of math today, but I promise it's not too bad. We can represent them in vertical brackets. And this means that implicitly it's what's called a column vector as opposed to a row vector. And the reason will become clear when we start talking about matrices. But you can see that these are different numbers, but again, these are two-dimensional vectors. It has two components, an x and a y, right? And well, what's some things we can do with vectors? Common vector operations. This is what you need to know about vectors. And a lot of these operations are fairly straightforward and intuitive if you are familiar with scalar operations. And I guarantee you all are, but you might not know what a scalar is. So anybody want to offer, what is a scalar? I say, oh, we're going to add these scalars. What am I saying? Yeah, it's just a number. In a sense, linear algebra is like a superset of all the math you already know, because you can reduce arithmetic to this sort of one-dimensional case. It's just a vector of size 1. It's just a number, and that's in linear algebra called a scalar for reasons that might become clear later on. Here's a hint, scaling, right? But the point is addition works the same. Now, kind of. What's happening here? What's a way to characterize, all right, 3, 4 plus 1, 2 equals 4, 6. If you had to sort of describe the algorithm, if you will, the pattern for what's going on here, how did we get 4, 6? Yep. We add across, add by position. Another way, I think maybe the most common way an academic might say it is it's element-wise. Addition is element-wise with these vectors. So we're adding element by element, and that this will also hold true for matrices, right? So and we'll be math people. We'll call this the first thing. I was going to say the zeroth thing because I'm used to Python and computer science, but we're adding the first number here to the first number there and getting the first number here. And similarly here, right? Now here we'll do it with code. And well, we actually have to start from 0 because we're switching back to that computer science Python list mode. So I know switching back and forth between, are we doing math? Are we writing code? It can be a little confusing, but it's good to take time to recognize that it's doing the same stuff. And if we run this, what are we doing? Well, we're making a list, which we're saying is a vector. And we know it's a list because on the outside here, there's the brackets. And there's 2 elements because there's just 1 comma here. So here's the 0th element, and here's the 1th element. And what is the 0th element? Well, it's just the addition of the 0th elements of the other 2 vectors, and similar here. And so we add the yellow and red, and we get orange. And it looks like this, 0.7, 0.6. And that makes sense because yellow was 0.5, 0.5, and red was 0.2, 0.1. So, by the way, if you're wondering what the heck is happening here, that's a good question that I won't go into right now, but numerical precision is a thing. What's happening here is computers are base 2, and floating point numbers are not. So, or at least with infinite precision, they're not. So really, this should be 0.3, 0.4. And a lot of times, if you were using not just native addition, but NumPy would actually probably ignore this. A lot of the scientific computing libraries will know to round this off. But any questions on arithmetic, vector arithmetic, the arithmetic version of it, just adding the numbers? Anybody, before I scroll down more, anybody know what the geometric picture is for vector arithmetic? If we take vector 1 and add vector 2, what do we get geometrically? So here's our geometric picture of just 3 individual vectors. Yeah, you could make a triangle out of it. These are good answers. You do get another vector. And intuitively, yes. So if you wanted to have like a geometric algorithm for what's going on, if I were to add red and blue, that would be equivalent to saying, take the red, which currently starts at the origin, and move its start to the end point of the blue. So we would travel down the blue vector, which would take us to here, and then we'd travel down the red vector, which would take us somewhere around here, right? And then the end result is actually the vector from the origin. So the end result is not this crooked thing, because that's 2 vectors, right? And that takes more than 2 numbers to summarize. We just want a single vector. So the answer of their addition is the single vector that starts at the origin and points up somewhere around. Can you see my mouse cursor? Because otherwise this is not going to make sense. Great. All right. That points somewhere around here. And that's the geometric interpretation. I keep on emphasizing all these different ways to see it, and I apologize if that's a little overwhelming, but I'm going to keep repeating them. There's only really these few ways. So as you start drawing connections across them, hopefully that'll help. So let's even sort of try to see this a little bit. Let's see if we have, so we're plotting a bunch of vectors here. So we're plotting, I think, our original vectors, and indeed, here's purple, right? And purple was red plus blue. And so indeed, if you go down the blue and then you picture yourself going down the red, and I'll say as a stretch goal, try to draw this, like try to draw another vector starting here to really see the vector arithmetic. But you could see that you'd end up here, and so it's purple. What would happen if we added in the other direction? If we added the blue to the, like we started going down the red first, and then we went down the blue. Yes, so in this case, you get to the same point. Vector addition is commutative, is the fancy math word for that. And that just means that A plus B is equal to B plus A. You can swap the order and it works out. That's what you're used to with nice friendly scalars, right? That is not always going to be the case for all operations in linear algebra. We will get to the significant counterexample later on. It is for addition, actually, but spoiler, multiplication will not necessarily be so friendly to us. All right. So now the purple and the green arrow happen to basically be on top of each other, right? Now, not basically, they are. And this actually brings us to those scalar topics. So really, you could say that green here is twice the purple vector. And let's step through this. So we did addition. Here's the other multiplying by a scalar. And how do we do it? Well, it's kind of similar to addition. We just multiply each of the elements, but just by the single scalar out here. And again, it's called scaling because we're scaling it. The geometric picture might be the best one here. You're just taking this purple thing and you're making it twice as long. And now it's the green one. And if we want to look at that, we can apply. We still get our little numeric error creeping in, but that's okay. Pretend this is 0.6. We can apply a lambda to double all the numbers in purple. And if we apply this, if we map it, that is, to all of the values in purple, and we get back a list, that list is green, and it's the same as the green vector that we already drew here. So any questions on scaling vectors? Now, let's think about this. And before I scroll down further, what would happen if I multiplied by a fraction that was less than 1? And like geometrically, let's try to describe it. Yes, it would shrink, it would shorten, it would, I think those are both fine ways to describe it. So if we multiplied the purple by a half, it would go around here. Now that's a good case too, but let's do this like Jeopardy. What is the situation for which something would go in the opposite direction? What would we have to have as the scalar multiple to reverse the direction? Negative, exactly. -1 would keep it the same overall magnitude, the same length, just swap it. So if you imagine it going the other way off the origin, we don't have this in our plot, but we could. Now you could both scale and flip it, right? You could multiply by -2 and make it bigger and the opposite direction, or -1/2 and make it shorter and the opposite direction, or any of these values, right? So let's just play around. I think it's just a crazy picture that lets us see a bunch of these options. I'll go ahead and rerun it, and let's step through it. So what we got here? We've got yellow shrunk, we've got blue grown, and we've got red reversed. And then there's a bunch of, again, all of these are really just Python lists. They're just two numbers, really. There's two-dimensional. And then we're using plot.arrow from matplotlib imported way up at the top. And you can step back through that, but in general, matplotlib is kind to us. And it might look like there's a lot of overhead here, and there is. Plotting stuff is picky. There's lots of parameters, especially if you want to make it look nice. This is a fairly nice plot. We've got some labeled axes, we've got labels, we've got visible axes, we've even got a title. All of these sorts of things require configuration. If you just tell a plot to plot some data without any of it, you'll just get the data, like you'll just get a line and not all this other stuff often. So I'm not going to step through all of what all these lines are doing, but let's focus, and you should though, by the way, but in our time in lecture, let's focus on what's happening with the geometry of it. So what do we do to, let me ask this as a question. So you see there's two blue lines, right? Can you see that okay? I'll zoom in a little more temporarily just to, I'll probably have to zoom back out, but there we go. So there's two blue lines. You can see one of them ends here, one of them ends there. Which one was the original and which one is the new one? I might have to look at the code to figure it out. Does anybody remember? Yeah. So no, it was yellow that we shrank. It was blue that we grew. So the original blue is shorter, is this one here. That's fine. And I was the one who zoomed in ridiculously. And the new blue is 3 times as long. And it goes out here. And that looks about right. But we were saying, okay, vectors can be represented by direction and magnitude. So what can we say about these two vectors? What do they have in common? What do they have different? And not that they're both blue. That's just how we happen to draw them. Mathematically. Yes, the direction is the same, sure. But the magnitude is different. That's what scaling does. And the same is true of all the others. So yellow, I think the original was the longer. So this copy of it is just half as long. And red, we just reversed it. Multiply it times -1, and it went out here. Let me get back out to a slightly... All right, there we go. Maybe one more actually works. Yeah, this works. All right. So now that we know what we can sort of do with vectors, we can add them and scale them, we need to think about a particular sort of vectors. Right now, these have just been arbitrary, like, okay, lines out from the origin that we're making into nice colors and talking about. That's great. But you might think, okay, what's the point? Well, we'll start getting towards the point by talking about basis vectors. A basis vector is how we define a space. And we're still going to keep working in this nice, friendly two-dimensional space, but everything I'm saying here is just as true for arbitrary n-dimensional space, for whatever crazy big data you throw at something. You still can think and use these terms and use it to sort of define and solve very important problems. So how do you make a basis vector? Well, let's start with 2D space. And before I go down any further, what two variables sort of come to your mind when you think about two-dimensional space? And go ahead and put on your geometrical hat here. X and Y, yeah. And usually if you draw them, how do you draw them? It's an X and Y plane, a Cartesian plane. Yes, length and width. We're starting to get to that. And it's okay to have these physical ideas in two-dimensional space. That's exactly why we're using it. Now, in 500-dimensional space, you can't have like 500-dimensional width. Well, you could, but we can't really think about it. Exactly, horizontal, vertical. So then here's a nice shiny picture of our X and Y axis, right? And so X is the blue axis here and Y is the red axis. So now how would you represent if, sorry, I'm trying to scroll ever so delicately. How would you represent the X and the Y axis as vectors? So it seems clear just intuitively that the X and Y axis define two-dimensional space. Like you've learned that whenever you like drew simple Y equals mx plus b plots, is this axis defined two-dimensional space for you and sort of implied everything else about the grids. So if we want some vectors if we want to think about this with vectors now, not just have it handed to us as infinite lines. Yep, 1 unit in X and 1 unit in Y. So let's go ahead and even like write those down exactly. So yeah, you could even just say any X comma 0 or 0 comma Y. Any of those would be a basis, but if you use the one here, which is just 1 unit, how would we write that one down? I'll start scrolling even, but keep typing. Yep, 1 0. Here's the 1 0 and 0 1. Exactly. And this is called not just the basis, but this is like the standard basis, the really conventional way of forming a basis of two-dimensional space. Because then, if you think about it, any properly scaled combination of these two vectors can basically define the entire space, right? If you scale and add these vectors, you can get any other vector, any point, right? Does that is I should try to come up with a better way to say that rather than just assert it. If you picture this as like an industrial site where the red dot can move up and down, it's like a big robot arm, and the blue dot can move left and right. Yes, they are independent of each other. That is pretty important. Then if you move the red dot, like let's say you wanted to get a vector pointing back here. Well, the first step is you move the red dot down here. How would we move the red dot down here? Yep, we scale it by negative whatever, 1.25 or something. And then I said down here, right? So how do we make the blue dot somewhere around here? It's similar, right? Scale it by about negative 0.6 or something. And then you add those two scaled vectors, and you get a single vector pointing to this point here. And you could do the same. You could pick out any point and pick the two and scale and add and get the vector. So that's what makes these a basis. That's how they define the entire space. Do we need, what if we had so I think this is stepping through it in a little more detail. I'll go ahead and run this. So plotting them as vectors, right? So these really are vectors. These aren't just dots. You can think of them as vectors, as we were earlier. And yeah, we have some code here that lets us, this essentially draws the picture and runs the code for what I kind of just described, minus the weird robot arm analogy, which is if we take our two vectors, our two basis vectors, x and y, and we scale and add them, we get all these other vectors that are pointing out all these other directions. And indeed, we could pick any specific vector, any direction, any magnitude even, and just we could put it together with this, right? So I'm not going to step through the code line by line, but it is here for your reference. Are there any questions on what a basis enables us to do, on how it sort of defines a space, generates a space? It is the basis for a space. Those mathematicians, sometimes they pick words for good reasons. All right, now we're on to what somebody hinted at earlier. Would this work for any two pair of vectors? So I picked two really nice vectors. But let's say we just picked any two vectors in two-dimensional space. Would it work? Could we still, just scale and add them and get any other vector? Well, it definitely works for some. It doesn't have to be the standard basis. Like let's say the first one is just twice as long. Instead of being 1, 0, it's 2, 0. That would still work. That would just change all the scalars that we multiply that one by, but you'd still be able to generate anything. Let's say they, well, sure. So the case of sort of the null vector, if you will, that's not going to get us anything. I don't know that would even really be considered a vector, but you could. Depends how mathy you want to be. There's one other problematic situation, though. Yes, they have to be linearly independent. That is exactly what I'm motivating here. But I'm guessing let's do this as a poll. I've heard of linear independence. So I'm guessing some of you have, and some of you haven't, and that's fine. You abstain. No, it's fine. Please share these things. I'm not asking you to, like if you studied this field, you can absolutely contribute. You can help your fellow students with homework. That is a part of the Lambda way. We are a school and a community. So, we try as instructors to help you, but there's more of you than there are of us. So you also get to work together. So let's talk about this. So it's correct. Yes, the two vectors need to be linearly independent. That's what it says right here. How can we summarize that? Well, actually, the geometric picture is really nice. These vectors are actually all independent. And that's because none of them are on top of each other. Now, you could argue that, it's not as nice to pick, the red vector and the purple vector as a basis because they're kind of they're at this weird random angle. But technically, yeah, you could, with the right linear combination of any of these vector of like red and purple here, you could get any other vector in two-dimensional space. The vectors that won't work for you is if we go back to these scaling pictures and we try the two blue vectors. What happens if we took the two blue vectors as our basis? What sort of space could we make with that? Exactly. Essentially, the second vector doesn't give us anything because we could already make either vector from the other one. So it's really just like we're getting one vector and we're really just defining a one-dimensional space. So sure, we could define any blue vector extending infinitely up and infinitely down in this particular angle, but we couldn't get any of these other vectors. And this is the geometric picture of what dependence is like. Now, there are many, many other ways to talk about independence and dependence, and we'll touch on a few more and many, many more in the full course. But for now, just think of it with the geometric picture. If you're not familiar with it, I think that's a good way to get started with the topic. So any questions on independence, basis? Because this is actually it for vectors. There's one last question to trigger thought here, but I'll ask you, do you have any questions before we talk about it? This is what you need to know about vectors for now. And I know this has all been with numbers, and I've been a little hand wavy about the real world significance, but while you think of questions, I'll try to conjure up a few cases. So, I mean, clearly expressing physical space works fine, but you could also think of each of these directions as being features. So you could think of perhaps the x dimension is the age of somebody and the y dimension is their income. And then a vector defines a single person based on their age and income. And thus being able to explore and manipulate these as mathematical entities will be useful. A projection of any vector onto any other vector. Yes, so we will talk a little bit. Let me see here. Yeah, I think we'll get to that. So I'm gonna defer for now, unless I accidentally skipped it. I don't think I did. We will talk a little bit about projections towards the end. And yes, so everything is 2D for now. That's a very good question. We'll get back to it. So here's a last question before we move on to matrices, though. I just said everything's 2D. Well, it is, but as a thought, how many basis vectors would you need to span 3D space? 3. Yes, this is not coincidental. I mean, this is in fact how a mathematical person would define 3-dimensional. And this is exactly why dimensions are this abstraction in math. You know, in the physical world, 2 and 3-dimensional space are kind of what we've got to work with here. But, you know, 500-dimensional feature space is something a mathematician can talk about, or at least hand wave about, right? Deploy their computer on. So let's move on to matrices. And really, now that you've covered vectors, here's some vectors, I hat and j hat, right? And there are friendly column vectors. So we're drawing them the math, or writing them down the math way that I introduced at the beginning. And we can just stick them together. This is now we see why they're column vectors. Let's say I hat is the first column, j hat is the second column. Hey, that looks like a matrix. That's the word for it. You know, a grid, a table, a spreadsheet. I mean, it's a matrix. Let's stick to that term in this context. But indeed, you can think of data stored in all those fashions as matrices sometimes. There are plenty of details, and I won't get into it now. We'll stick with pure friendly numbers for the time being. But that's all the matrix is just sticking multiple vectors together. It's just a collection of vectors. And so if a list is how we represent a vector in Python, say, how are we going to represent a matrix in Python? Mm-hmm. Yep, a list of lists, sometimes called two-dimensional arrays or other things in other contexts. But the most Pythonic way to talk about it would probably be to say a list of lists. Now, really, we're going to use something called NumPy, which is a little more optimized than Python lists for these specific sort of operations. But for now, we're building it up from first principles. So if you can kind of picture, and it really just is exactly, it's like, so there's the starting brace, and then, well, let me even type this one, and I'll type it as column vectors, 1, 0, and then 0, 2. And I'm putting those spaces in there just to make it easier to read. You don't have to, but that would be a sort of Pythonic way to represent it. You can, there's nothing stopping you from putting lists in Python, or other languages for that matter. Now, what can we do with this? Well, we can take this matrix that we've got, and we can multiply any vector with it and get a transformed vector. Now, can you see what's going on? It's being stepped through here. But essentially, the way we do it is we take each value of the column here, and we multiply it times the corresponding column of the matrix. So, sorry, we multiply and add to the others, yes. So this is where linear algebra starts getting confusing, but this is a good simple example. So I'm going to stay on it for a little bit and let you follow through the steps. So how do we get this top 3? Well, it's from this 3, the top value here, times 1, 0, the first column. And what do we do with that? Well, we multiply 3 times 1, and we also multiply 3 times 0. But then we're not just actually scaling it. We're not just getting 3, 0. We add it together, and we get the single value 3, and then we stick it back up here. So that's where this 3 comes from. Where does the 8 come from? Well, again, now there's the second value of our output. So it's from the second value of this. And is there a typo in here? It looks like it is a 4 times 0, right? Or hold on. Oh, you're right. Oh, yeah, you're right. Actually, this is an ambiguous example. I'll go ahead and correct that real quick, though. I'll find it and correct it afterwards. The point is, maybe I should find it right now just to get it in the right spot here. So this is called LaTeX, and this is a lovely. So this should be a 4, and this should be a 3, I believe. Yeah, or no, that should keep being a 4. This should be a 3. You're right. It steps through slightly differently than I was describing. Thank you. So as you can see, multiplication is actually tricky. And remember when I was saying earlier that not everything is commutative? Well, yeah. Multiplication in linear algebra, you can't just swap the order. What's coming on the left and what's coming on the right matters. And the reason it matters is because it determines what you pick out as a column versus what you pick out as a row. And in general, the way you want to do it is the output. So first off, the second dimension, the number of columns in the entity on the left has to be the same as the number of rows. Sure. Well, 4 times 0 is still correct, so I'm going to leave it at that. Why did that refresh? The number of columns of this matrix has to be the same as the number of rows here, which it is. There's 2 columns, there's 2 rows. And then the output will have the number of, let's see if we get this right. Basically, it's going to have the same number of rows as the first item and the same number of columns as the second item. So what we're saying is that to multiply 2 things, to multiply an m by n times an n by p, and this is row by col, n has to equal n, right? So the first thing has to have as many columns as there are rows in the second thing, and the result will be m times p. So that's a little bit of an algebraic way to understand it, but hopefully that helps. And we'll just keep, you're going to be doing a lot of practice. That's how you get this. You just do it by hand, you do it multiple ways, and you pick it up. So what's happening here? Well, we have this row, the first row, times this column. The first column gives us this value, times and added. So 3 times 1 plus 4 times 0, and that gives us 3. And then the second one is, again, determined, it's in the first row of the output, so it takes the first row of this, first column of the output, so it takes the first column of this times the second row of this. I know I'm getting a little bogged down in dimensions, so I'm going to keep going and we'll revisit the examples. But the point is once you wrap your head around matrix multiplication, you can actually do it more broadly. You can split columns, and essentially, how do you multiply 2 by 2 by 2 by 2? Well, you can first imagine multiplying the first 2 by 2 by a 2 by 1, and that works as we discussed above. And then multiplying the same 2 by 2 times the second column here. And those two columns you get as output correspond to the first column and second column of the output, respectively. So I'll encourage you to step through these examples. I'm going to keep moving so we get to the end of the material at 6. Learning matrix multiplication takes more than an hour. So if this feels like a lot, that's okay. Keep working at it. The good news is we have NumPy. So this is one of our brave libraries that we've got. NumPy will handle multiplication, though that's not what this code here is showing. So we're going to start in this by talking about one other important matrix concept that you should be aware of called the determinant. But before I continue, any questions about matrix multiplication besides the fact that it probably doesn't make sense yet, but are there any particular questions about these examples? If you just step, it is just arithmetic. It is just multiplying and adding. As long as you know the right thing to multiply and add together, you can multiply matrices, as long as the dimensions work out like I described. And yes, exactly, as we'll get to later on, essentially what we're doing is, another way to say it is the ij member of the output. Double clicking does that. The ij member of the output is the dot product of the ith row and the jth column of the input, as you will, the things being multiplied. So the ij, so this is row 1, column 1, corresponds to the dot product of the first row and of the left and the first column of the right. And then 1, 2 here corresponds to the dot product, 2, 1, this is row 2, column 1, I did get it right. 2, 1 corresponds to the dot product of the second row and the first column. And dot product is this operation here. It's shown again at the bottom of the notebook, so we'll step through it then, but it's where we're multiplying the elements and then adding them together to essentially collapse them back to a single value. So it's another helpful way to think about it. You're going to have to just do these by hand, and that is part of the homework. And if you do enough of them, you'll pick up on them. And yes, MATLAB is natural for this, and if you have MATLAB experience, maybe check out that resource Mark just dropped. So, on to NumPy. NumPy is great. NumPy does all sorts of numeric things for us, generally speaking, linear algebra things for the most part. So it has a concept of arrays and matrices, and we can define matrices and see what they look like. So we can define and we can use this sort of compact, we don't have to use all those, like, remember how I was talking about how, oh, you'd have to do like this, and then, you know, something like this. It's fewer characters. You don't have to use all these braces. You can just say, hey, here's my first row, here's a semicolon, here's my second. And yes, these are rows, not columns. That's just because that's how this particular norm for entering it works. But you can think of it either way. And if you print it, you get a nice little picture to sort of see what it is. Yes, you're right. Multiplication of vectors gives the cross product, not the dot. Yeah. So what can we do with these? Well, we can plot them. And in particular, if we do plot these, we get this kind of cool picture. What's going on here? Well, we can see, if you see, and it's down here as well, it's up against the axis, so it might be a little tricky to see. But we're plotting a matrix based on its two vectors, right? So we've got, does this correspond to one of the rows? I think, yeah, 3, 4 is one of the rows. And let's see here. Actually, no, these are the columns. 3, 1 is a column, and 4, 6 is a column. And the matrix then is this whole sort of space here that you can fill in if you envision it that way. Not the matrix, sorry, but we're talking about the determinant of the matrix. The geometric intuition is that it's the area that corresponds to the matrix. So this down here is sort of like a nice friendly unit or near unit matrix, right? It's just sort of nice and friendly, and it just takes up a little box here. This one is a much bigger transformed sort of matrix. And so this one has a determinant of 2 because it's 1 wide but 2 high. So, a matrix with a determinant of 1 would be a matrix just made from the 2 standard bases, 1, 0, 0, and 1, 0, 0, 1, right? And that would have a determinant of 1. Determinant of 2 because it's twice as high. This one has a determinant of 14. And it really does correspond to how much area there is here geometrically, the scaling in a sort of multidimensional sense. So we talked about scaling of like single vectors. Well, this is like the scale of the matrix itself. How do we actually get it? Well, getting determinants is complicated in the general case, but in the two-dimensional case, you multiply the main diagonal and you subtract the product of the off diagonal. So 3 times 6 is 18, minus 4 times 1 gives us 14. So the determinant of this 2 by 2 matrix, this blue one that we're representing here, is 14. And intuitively, yeah, it's basically 14 times a little unit matrix down here, if you can picture that. I promise I'll get to applications a little bit, or promise of applications in closing. I know that I'm just throwing a lot of math at you, but does this make sense? Perhaps more sense than matrix multiplication, at least. Yeah, I think of it that way geometrically. The scale that it has to scale, the scale that it has to scale, that's great. If you picture the unit vectors, the scale that you have to apply to them to get the overall matrix. And what happens if you multiply? Well, you can multiply matrices together and then get their determinant. And what is their determinant going to be? Well, again, it's best understood visually here. So if you multiply this matrix, so this was the one that had the determinant 14, times this matrix, which has the determinant 2, you get this green matrix. And it turns out that the determinant of it is 28. That's suggesting something. How could we have calculated that without going to all this trouble of drawing a picture and everything? Yeah. So essentially, yeah, the determinant of the products is the product of the determinants. That is a law of sorts. I'm not going to prove it, but you have a visual illustration here, and it kind of squares with the intuition of thinking of this as a sort of area or multidimensional magnitude or something. If you multiply them together, the thing you get is the product of the things that you threw in it. And it's a nice property of determinants. Now, determinants have some other nice properties. So what happens if determinants are 0? So there's a lot here. I'm not going to unpack all of it, but we've got, I think, a purple and a yellow here that kind of overlap, and then another like yellow and a blue that overlap. And if we try to calculate the determinant of them as a matrix, we get 0. And what is that saying? Well, that's saying a lot. This is sort of getting to the applications. The reason we care about determinant, not just to draw cool pictures, but because a determinant is an important number to ask about a matrix because it will tell you important things. It's a single number that you can just get, and fairly efficiently, even though it's a little complicated. It's a fast calculation to ask for. And essentially, just asking whether or not it's 0 tells you a lot, because if it's 0, essentially you're in a lower dimensional space. So what this means is a determinant for a matrix is 0 if and only if the column or row vectors are linearly dependent. So that's why we have this picture here with the things lining up again. They're just products of one another, is what we're saying. And essentially hopefully this works for you. It works for me. You could think of it as like the matrix doesn't fill in the shoes of its dimension, right? So this is claiming to be this second dimensional matrix, right? It's a 2 by 2. That should be a 2-dimensional matrix. But it actually isn't. It actually, the two vectors that make up the matrix depend on each other, so you may as well just have only one vector. So why do you even have a matrix, right? It doesn't have the rank, is the mathematical term for how many linearly independent vectors a matrix has. So a matrix has full rank if all of its vectors are linearly independent, if they are not just overlapping like this. But if they are dependent, if the rank is less than n, then it's not really the full dimensionality of it. And so that's why later on you'll see techniques to sort of, okay, we need to do these things. We need to do things to matrices to make them this way sometimes. And one last motivating reason, which will really come to play tomorrow when you learn about applying this to actually make models with linear regression, is this sort of matrix that has a determinant of 0 is not invertible. Now, why do we care that a matrix is invertible? Well, inverse is the last matrix operation we're going to talk about, and it's a big one. And you can think of it as sort of related to division, right? We've talked about addition and multiplication. Let's talk about inverse, which is, it's not exactly division, but it's like it in spirit. I mean, let's think about numbers. What's the inverse of the number 10? Oh, sure, multiplicative inverse. Clever Mark. That's the additive inverse, 1/10. What do I mean? Multiplicative inverse versus additive. Well, multiplicative means if you multiply it times its inverse, you get 1. Additive inverse is if you add the two numbers together, you get 0. But we're dealing with a more multiplication type question here. So the inverse of a matrix then is the matrix that if you multiply it by, you get what's called the identity matrix, which is this special matrix here that's just 1 down the diagonals, and that's it, 0's off of it. And I'm not going to motivate why it's special now, just know what it is and be able to recognize it. But the determinant gives us a way to get this inverse. And how do you get there? Well, if you have A, B, C, D, and you want its inverse, that's what -1 is, then that, and this is a special approach for the 2 by 2 case. This is not a general approach for all, rank matrices. But essentially we're saying it's 1 over the determinant, which, remember, what's the determinant? What's our formula for the 2-dimensional case? If we want to say it in these terms of A, B, C, and D, it's A times D minus B times C. So it's 1 over that number. So it's pretty clear why you don't want 0, right? You can't divide by 0. 1 divided by the determinant, and then times, just as a scalar, this magic thing that I will not solve for now, this rearrangement of the original numbers, D and A. So you're swapping numbers across the diagonals, and you make these ones negative B and negative C. And if you do that, you get the inverse. So actual example, what's the inverse of 1 and 2? Well, the determinant is 2 minus 0. So 1 over the determinant is a half. So it's a half times these numbers swapped, and then -0, which is just 0. So a half times these numbers swapped gives you 1 and 0.5. And then I encourage you to step through this step by step and try to to practice your matrix multiplication. We all should practice our matrix multiplication. But indeed, if you multiply our original matrix times its inverse we calculated, we get, okay, 1 times 0 plus 1, sorry, 1 0 times 1 0 gives us 1 plus 1 plus 0 times 0, which is 1. And then etc. down to, we'll get zeros in the off diagonals because of the zeros in the off diagonals here. And then this one comes from 2 times 0.5. So it's not just multiplying the elements, I should say, but it kind of reduces to that in this case. Now, NumPy gives us a magic one-line way to do this. So you don't have to do this from scratch all the time. We're making you step through it once in a low-dimensional case to build the intuition. But in practice, NumPy has linear algebra routines, including inverse, and if you feed it a matrix, it will give you the inverse, and you can print it out. And if you multiply it, you get, well, again, this is essentially 0, right? It's something times 10 to the negative 17. So this is a rounding error. But you get the identity matrix, 1 times the main diagonals and 0 off. So, you also get matrix multiplication. So yes, do step through it. That's part of the homework. But in practice, especially for bigger matrices, use the routine. And now we're almost out of time, but I'm almost to the end of the notebook. So almost on schedule. There will be applications for this tomorrow. That's what I want to say. I know that I'm just giving you linear algebra in isolation right now. You will learn about something called linear regression and how it is solved with linear algebra and how it makes some of those really cool inferential statistical models that we mentioned last week. So if you wanted to be able to predict the price of a house based on its age and square foot and so forth and so on, that's a technique to get started doing that sort of thing. And the math goes down to this. So this is a little bit more review material on dot product, so I'm not going to step through it, but I encourage you to, in your copy of the notebook, play with this and review it in the context of matrix multiplication. So I'm just going to sort of keep going for the time being, but if we print a few other operations that matter, there's matrix transpose. So this is our original matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9. What does matrix transpose do? Anybody figure out what we did to get this second matrix from the first one? Yep, we turned it sideways. Exactly. The first row becomes the first column. The second row becomes the second column. The third row becomes the third column. Exactly. It's a useful operation. It will be relevant in other contexts. And yes, you could also picture this as flipping by the main diagonal, right? Because 2 and 4 changed places, and 3 and 7 changed places, 6 and 8 changed places, but 1, 5, and 9 all stayed the same. So you could picture it as this sort of triangular swap. And then the last thing is is it the last thing? Pretty much the last thing. And then some species of matrices. Vectors are orthogonal if their dot product is 0. So this is getting to the projection question that was asked. So I should at least say a little bit, what is a projection? Well, if you wanted to project, if vector x is the unit vector here and vector y is this vector that goes up to 3, 2, the projection of y onto x, which you calculate using the dot product, essentially goes down to here. It goes to 3, 0, which is if, it comes down until it hits where this vector would be, right? And what if we tried to project these vectors onto each other? So we've got this vector 1, 0, and this vector negative 2, 2, right? No, 2, negative 2, sorry. 1, 1, and 2, negative 2. And let's say we wanted to project this vector, this blue one, onto the red one. We're like, okay, we're going to go off the blue one until we hit the red one. Do-do-do. Do-do-do. Yeah. You're never going to intersect. They're perpendicular, or orthogonal is the way to talk about it in the linear algebra context. And so the projection off this will be parallel and never intersect this guy here. And so this now, remember when we talked about the standard basis? The standard basis is usually orthonormal. Ortho because it's orthogonal, and normal because it's the standard unit length, right? 1, 0, and 0, 1 are orthonormal vectors. But this is how we can define what orthogonal vectors are. And then what's the point of all this? I've talked about this enough. You can read this as you wish. And this is also the note that multiplication is not commutative. You can't swap the order. The order matters. This will all build into stuff you'll see tomorrow. Any questions before I give a few fun pictures, links, and get you on the homework? I know it's like a lot of material. Please, if nobody absorbs all this stuff just all at once like this, but we give you the resources to keep coming back to it and studying it and asking questions. That is a critical part of the learning process. That is just as important as being here at the lecture and participating. So do that. Revisit it, ask questions. Any questions now are welcome. And if questions occur to you later, ask them then. In the interest of not holding you late, these are just pictures of matrices you should know about. I'm not going to formally define them, but the picture is hopefully illustrative. These are triangular matrices. Anybody have thoughts for why they're triangular matrices? And I know these aren't numbers, but just imagine that there's some numbers where they're green dots. And these are all zeros. Exactly. Yep. So it's, and you could have positive or negative numbers here potentially, but exactly. Basically, there's a triangle with numbers, and then there's this lower triangle here that's just, I mean, zero is a number, or is it a philosophical concept? But whatever it is, it's usually not, you know, it doesn't result in much. So these are all zeros, and this would be an upper triangular matrix because it's populated in the top, and this would be a lower triangular matrix. It's just a sort of matrix that if somebody says what it is, this is what it is. What about diagonal matrices? Well, that's just when you only have numbers on the main diagonal and everything else is zero. And note, these do not have to be square. If they're square, then it's also symmetric. Why is this a symmetric matrix? What does that mean? Yeah, it's the length equals the height. And what is the transpose of this matrix? Exactly. A symmetric matrix is a matrix where the transpose equals it. And that is the case here. Now, there are symmetric matrices that don't have zeros here. So not all diagonal matrices are symmetric, and not all symmetric matrices are diagonal, but all square diagonal matrices are also symmetric. And then you can have non-square diagonal matrices where you just have the main diagonal populated for as far as it goes, and then just zero vectors for any remaining rows or columns that make it rectangular. And then the last special species of matrix we'll talk about are identity matrices, which, yes, even reduce all the way to the scalar case of the number 1, but also have 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, ones down the main diagonal, zeros everywhere else. So they're a very special diagonal matrix, and the reason they are is because any matrix times the corresponding identity matrix of the same dimension, any square matrix times an identity matrix equals the original matrix. That's why it's called the identity matrix. And I'm not going to talk about why, but step through it in a 2x2 case to practice your matrix multiplication and to see why the identity matrix is special. A lot of other terms, I just threw them out here for reference. Do not feel like you need to know all these. I would not be able to define all of these off the top of my head. But they're all related to linear algebra, and you might encounter them if you try to go deep in this field. You do not have to go this deep to do data science, but if you want to specialize in numerical routines and optimizing calculations, you can study all sorts of stuff. Linear algebra is a very deep field. And that's what these resources are about. So here's a little joke about rotating matrices. It's an XKCD comic. This is not how rotating matrices works. You don't just spin them on their side like that, but we can pretend. Tomorrow, as I mentioned, we'll be applying this to regression. That'll be really exciting. And for some resources, you can read more about what a zero determinant's like. There's a hacker's guide to linear algebra, which covers a lot of the same stuff I covered, but with a pretty direct application to deep learning, just another treatment of it. There's hacker rank exercises with NumPy. do the assignment first. But if you get that done, you're like, I need more NumPy practice. Here you go. And then this is a major commitment. This is a semester-long course. But if you want to learn linear algebra, this is one of the better resources that's out there. MIT's open courseware on it. So, any questions? Sure. I'll try to scroll up. I might have moved my mouse a little incorrectly, which might be what your question is about. Yeah, essentially, yeah, because that's basically the corresponding, if you're represented in Cartesian coordinates and you're trying to project it down to the x-axis. Now you could project, there's nothing that says you have to project onto the x-axis. You could project a vector onto any other vector. But yes, the standard basis, if you're projecting down to that, that's why we use these things, right? While you ask questions, I'm going to go ahead and get this link to share. This is the assignment for tonight and beyond. I'm not expecting people to finish it, but work on it tonight and submit it in the stand-up form. All assignments are due November 1st. So keep typing your question, but while you type, just to describe the layout of the assignment, these short answer questions should actually be answered in your own words. So just, you can make your copy, you can double click here and you can type in English. You don't have to type code, just type your words to describe these concepts, to practice them in your head. And these computations you should solve, perhaps even with pencil and paper, and then type in. There are some descriptions that you can just, type it with text like this. You don't have to make it pretty the way we try to do some, but if you want to try to learn about making it pretty, that's a stretch goal. And this will just give you practice adding and multiplying and transposing and inverting things. Then the actual Python will be to essentially do stuff similar to in the lecture notebook. Make some vectors as Python lists and draw them and scale them and draw the scaling of them. And graph the columns and rows of the matrix. So you can think of this as column vectors, 2, 3, 2, 1, or row vectors, 2, 2, 3, 1. Graph all those vectors. And then lastly, after we make you suffer by doing everything by hand, you get to redo all of this, but it'll be easy, I promise, because you can just use what NumPy gives you. So that's the homework. In the example, I wasn't sure whether x0 would give the projection on the x-axis or the projection onto the red line. If I look at the example again, I think you'd think of it as a projection on the x-axis, but yeah, we will revisit that. I'm already 10 minutes late, so thank you for your time. Get to work, and 7 o'clock, keep an ear out for the PMs. And Susanna, if you want to pitch into Quinn's question here, since you prepared this example, that would be great. All right, thank you, everybody. It's a lot of fun. Stick around and keep working tonight and be here tomorrow, and I promise you'll see exciting applications of this. Thanks, everybody.